Kia ora and welcome to the screencast for Workshop 8 for 161324 data mining. So this week we're looking at regression classifiers. So we're looking at logistic regression for the case where we have a binomial response, so a two-class outcome variable, and multinomial regression when we've got more than two classes. So for logistic regression, we're going to look at some data on colic in horses. So colic can be quite a serious illness for horses and can result in death. And we have some physiological data on 368 horses where colic was recorded, along with whether surgery was required, and some of the horses died and some survived. And the goal is to train a logistic regression classifier in order to classify the horses into whether they're likely to survive or die based on those physiological parameters that we've measured. So we'll start by reading all the packages and so on that we'll need. So obviously we've got the tidyverse for ggplot and dplyr and all that. We've got rsample for splitting the data set into a training set and test set. We've got skimr for looking at the data. We've got discrim for doing our discriminatory work, so for logistic regression, for example. We've got yardstick for measuring how well we do. We've got recipes for processing the data. And you'll notice that one of the things I do here is I take I redefine the step function. And the reason I'm doing that is that we're going to use step for stepwise regression, and that's in the stats package, but the recipes package also defines the function step. All of the steps in your recipe are based on the step function, and therefore if we just ran step on a model, it's going to be using the recipes version of step because the recipes library was loaded after the stats library. So we're overriding it here in a very simple way, just by redefining the step function to be the step function from the stats package. Okay, so we've got the horse data. We could just have a quick look at it. Okay, and so we can see that we have some 11 grouping variables, factors, and 5 numeric. So here are the factor variables. So we've got whether surgery was performed or not, and so on and so forth. Whether they died, that's the outcome. And then we've got some numeric measures as well. So we're going to use the logistic regression. So we could build our model. So we're going to use a logistic regression with the GLM engine, which is the default. And we could then fit died to all the others variables using our training data. Okay, we could have a look at the summary output. So we could either do extract, so if we have a look at horse.lr, of course it'll be a parsnip object, and we can get some information on the a summary of the coefficients here, but if we want the proper summary, a summary function I think won't work. Let's check. No. So the summary function gives us something different here. It's not what I was expecting, and we've got to extract the fit engine to get the underlying GLM object. And then we could do the summary. So there's the summary. So you can see that many of these factor variables have multiple levels, and there's some significance here. So there's some significance for the pain variable. We also see age is significant. Let's look at the coefficient. So we've got a coefficient of 3, almost 3 there. And so that means that because it's a positive number, then that means that if they're in the old age group, then they're more likely to die. So the response variable was died, yes or no, or 1 or 0. So the second class is that they died. So a positive coefficient is associated with death, which makes sense, right? If the horse is old, then they're more likely to die anyway. There's also a slightly positive coefficient for packed cell volume. So as the packed cell volume increases, there's more chance of death, and so on, right? So there's some, let's have a look. Are there any real protective factors? None that are really significant, I don't think. In terms of, so I'm looking at the stars here to see whether there's anything that's associated with a negative value. I don't think so. So that's the output there. We could also do this in a tidy way with using the broom tidy function, right? And it'll give us the oh, do I have to? Yeah, broom tidy. I don't think I've loaded the broom library as the reason why that didn't work. So here we can see that we get the same information in a data frame form, and that's useful if you want to filter on the p-value or whatnot. Okay, same information. Okay, so this next part we're asked to compute the odds ratio for the surgery predictor. Does having surgery increase or decrease the odds of the horse dying? Okay. So to do this, we have to understand what an odds ratio is. I don't think I went through this in the lecture, but of course it is available in the notes. And the idea is that the logistic regression is modeling the outcome variable 0, 1 using a probability. So it's a Bernoulli distribution or a binomial distribution with n equals 1. It's like tossing a coin where the coin is weighted with some probability. And then we model the log odds of that probability with a linear predictor, right? So the actual linear predictor is that if I write it in maths, would be log of pi on 1 minus pi, where pi is the probability, is going to be that linear predictor, right? So we're going to beta 1 surgery plus beta 2 something plus a bunch of other stuff, right? Up to say beta p or something like that. Let's use k. Right, so here's our formula here. Obviously, you don't need to know how to write this, do this fancy maths stuff. This is known as LaTeX, or another form is MathJax, which is actually what's being used here. But it just means it's just a way to write mathematical equations using plain text, or perhaps not so plain, I guess. And so this is the formulation of our logistic regression predictor, right? We've got this linear predictor here, which contains our term that we're interested in. And that's what's used for the log odds. Now, this is odds. So you remember that the odds are a probability divided by its complement. So if you're like 1 minus that same probability. And so this kind of makes sense. Is if you've got, so say the probability is a quarter, right? So the probability of something happening is a quarter. Then the probability of it not happening would be 3/4. The odds of it happening compared to not happening would be a quarter compared to 3/4. And that's often expressed as a ratio, which is be one quarter divided by 3/4, which is 1 to 3. Okay, the odds of it not happening would be 3 to 1. Right, so the probability was a quarter, but the odds are then 3 or a third. Okay, because of this formulation. And so this is the odds, and the linear predictor is for the log odds. So what does this mean in terms of this coefficient beta 1? Well, if surgery is so if a horse has surgery, then its odds are expressed using, so if it has surgery, then the surgery effect is 1, and so we're going to have 1 here, right? And so the log odds is given by that formula there. If a horse doesn't have surgery, then surgery equals 0, and this term here is now going to be 0, so we lose the beta 1. Okay, so beta 1 is capturing the difference in log odds between having surgery and not having surgery. Okay? So that's what beta 1 is capturing. So that's what beta 1 is telling you. So the effect, we could have a look at what it is, right? It's 0.389. So that's telling us that the log odds of death increases by 0.389 when the dog has had, when the horse has had surgery, compared to if the horse didn't have surgery, right? So the surgery effect increases the log odds of death by 0.389. Now, unfortunately, the log odds isn't something that's particularly intuitive to us. We perhaps the odds might be more intuitive. So what's the effect on odds? Well, we'd have to exponentiate these two things, right? So what about the odds? Then the odds of death when a horse has surgery would be, well, all we'd have to do is exponentiate that formula. All right, so we're just going to get, we can get rid of the log by exponentiating that formula. Okay, we're going to have a beta 1 in there. And the odds of death when a horse doesn't have surgery would be same thing, but this time without the beta 1, right? Right, so same thing, but without the beta 1. So the change in the odds can be found by dividing one by the other. Right, so let's maybe say this is P surgery, or maybe call it PS for surgery, and this would be doesn't have surgery, so we'll do PN for no surgery, right? So the change in the odds can be found by dividing one by the other, right? The ratio of the odds, right? So we could do one over the other, right? And that's just going to be this divided by this. And if you think about it, when you divide one of these by the other, the difference in the exponent here is just beta 1, right? So this is like 10 to the power of 6 divided by 10 to the power of 4 would be 10 to the power of 2, right? It's just the difference between the two powers, and the difference between the two powers here is just beta 1, right? So this is just going to be e to the beta 1. Okay, so the odds ratio is the effect on odds. So it's the change in odds for that term, computed using the exponential of the coefficient. Right, so now that we know what the odds ratio is, we can compute it, and then we'll look at the at how to interpret it. Right, so we can use the tidy form here. Okay, so here's our coefficients, and all we want to do is we want to compute the odds ratio, so we could do that with a mutate. The odds ratio is just the exponential of the estimate. And then we could filter term surgery 1, or perhaps find surgery, and then we can see the odds ratio there. Right, so surgery has an odds ratio of 1.48. The interpretation is that if a horse has surgery, its odds of death has increased by 1.5 times. Right. So essentially, the odds of death is increased by 1.5. Okay, so this means surgery this means that horses that had surgery were more likely to die, around 1.5 times, than horses that didn't. This probably makes sense, right? As presumably horses that have surgery were perhaps in worse shape than those that didn't require surgery. Right, so if surgery was a consequence of the of colic, right, then you might think that that horses that were in bad shape were more likely to be operated on, and therefore were more likely to die, just not because of the operation necessarily, but just because they were in worse shape. We don't know. I mean, the surgery may actually be to do with something else. Who knows? Okay, so now we can have a look at the predictive performance on our test set. All right, so we've got our model here, and we could then augment with our training data. And then we could have a look at the accuracy. So the truth would be whether they died, and the estimate would be our predicted class. Okay, so we're getting 76% of them right, and we could also have a look at the confusion matrix. As well, and we can see that we're getting slightly more of the ones that died wrong than we are getting the ones that don't die. So the one is died. Okay, so our overall accuracy rate, 76%. I think I got that, remembered that correctly. Yep. And slightly more we're getting those that died are wrong more often than those that didn't die. So perhaps this might not be ideal, because presumably the goal would be to try and prevent death, right? If this was, deployed in practice, so you'd want to be making sure that you got that your prediction of no death didn't include too many that actually died, right? So we'd want to reduce this number 14 a bit, even if that meant that we were predicting that some would die, even that, if it meant increasing the 8 a little bit, right? Because that's not so bad. We'd be predicting that the horse died, and maybe that then would result in some sort of closer look at the animal, but may not necessarily change the outcome for that animal. So we'd kind of want this number to be bigger and that number to be smaller, I would think, if we were using this to sort of screen horses for likely success rate. So we've got a very big model here with a bunch of variables in it. Perhaps we could get away with a smaller one. So we might try using stepwise regression. So we could try just running step on our model, and we'd have an error. Okay, and the reason that we get an error there is that the stats step function doesn't know how to deal with a tidy models object, so a parsnip model object. You might try extracting the fit engine to get the underlying GLM object, and then trying step. And you can see that it starts but quickly stops again, quickly fails, and that's because it doesn't have the correct data. And that's just a consequence of how the model is fit. So normally if you just fit a logistical regression using GLM, then it will actually tag that data into the resulting model object, so that when you run step, it's got the original data to pull from for refitting the model with other covariates. Parsnip doesn't pass the data on in that way, and so it's not allowing the GLM function to store the data in the same way, and therefore step won't work. So we're going to have to go sort of old school, backward GLM, right? So we're going to fit the model with GLM. So this fails as GLM doesn't have the training data embedded in its model object as okay, so we'd have to go family equals binomial, and then data equals our training data. Right, so we should get the same model. So this is going to be horse.lr2. Okay. So if we do a summary on that, we should get the same numbers, right? So these the same number that we had before. Okay, everything's exactly the same, but now we can use step. Or stepwise regression. Okay, and it goes and runs, blah, 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 and eliminates a bunch of variables, right? So we get down to one using only these variables here. Okay, so now we want to know, well, how well does the second model do? And because evaluating model fit without tidy models is a bit awkward, what I'm going to do is I'm going to refit the same model using tidy models. All right, so horse.step in the tidy models framework is going to be the result of a logistic regression where we fit and we could just copy and paste the formula from there. Okay, and away it goes, and then of course we can do our prediction as per usual. So augment new data is going to be our test data. Okay, and then we could work out the accuracy. Okay, we're doing exactly the same by the looks. And then we could also do a confusion matrix. Okay, so slightly different. I think this is probably better. So instead of that number being 14 and 8, it's now 13 and 9, right? So our overall accuracy is the same. Things have changed a little bit in that we've traded some false. So this here is going to be a false negative, and this here will be a false positive. Some false negatives predicted survival actually died with false positives. Predicted died actually survived. This is probably a good thing. We could try and find out exactly what has changed, because what we could do is we could look at the individual predictions, right? So what we could do is we could go by joining these together, right? So we could go horse.prid, right? That's our first prediction. We could just pull out, let's have a look. Let's see what that looks like. Really, we want the we want an identifier, don't we? So that we can join the two data sets together. I guess we could bind them. We could select, because the row order will be the same, won't they? So we could select so we could say prediction 1 is the predicted class and prob 1 is predict 1, and then we could bind columns. Well, we could just go with force.pred2, couldn't we? Right, so here we have the predicted class for with our first model, and here's our predicted class with the second model. And we can see that they're the same, aren't we? Okay, aren't they? Mostly, but we could find that one's different. So here's one that's changed. And we might want to perhaps plot the predicted probabilities against each other. So we've got the probability of death here. So we could do a scatter plot. So we could go x equals prob 1, y equals .pred 1. We could maybe that's probably actually all we'll need. Let's try that first. Okay, so here's our two prediction probabilities plotted against each other. I guess we could colour them based on whether pred1 was equal to the predicted class in the second one. Right, so here we go. So you can see that the blue band here is the ones that we've got where the predictions are the same, and the red points are the ones where they differ. Okay, and so you can see that the red points are essentially where we have they're around about the probability 0.5, right? So if prob1 is bigger than 0.5, then we're predicting death, right? So for all of these red observations here, we're predicting death with prob1, which was the first model, but we're predicting they survive in the second model, right? So this is the second model here. So these ones have been predicted that they survive in the second model, and these are the ones that we predicted in the first model that they would survive, and in the second model that they would die, right? Because dot pred1, that was from the second model, is bigger than 0.5, and prob1 is less than 0.5 for those observations here. So we basically gridded it. I guess we could put some lines on it so we can see what's going on. We could go geom h line. X-intercept is 0.5, it'll be a y-intercept, won't it? And geom v-line, x-intercept is 0.5, right? So up in here, we're getting them, both probabilities are more than 0.5, so we're predicting death for each, from both models. Down in here, we're predicting survival from both models, and these ones are the ones where we've got an inconsistent result. And the idea is that that inconsistent result largely affects the ones that are around the crossover, right? They're not going to affect ones where, the second model was super confident that the horse was going to die, while the first model was super confident that it was going to survive, right? That's unlikely to happen. The two models are generally going to be in an agreement. Okay, so there's 9, 10. Right. 4 where model 1 is predicting death while model 2 predicts survival, and 6 where model 1 is predicting survival while model 2 is predicting death. Okay, so you can always compare your results by contrasting or plotting your predictions for one model against another, and it's sometimes a useful thing to do to get a sense as to where your models are going right or wrong. Okay. Right, so for the second example, we're looking at classifying some wine data. So this is the data from the notes and the lecture. Okay, so let's have a look at it. Okay, so we have our cultivar, which is the class of interest, and then we've got a bunch of measurements here. And the first thing I note when I look at these is that they're all numeric, but they're all on different scales. So for instance, proline here is on a different scale than all of the others. So when I fit a multinomial regression, I'm going to be wanting to scale the data because it's using the neural network package to do the fitting, and therefore there's that exponentiation step that is done in the sigmoid function, and if the predictors are on vastly different scales, then that can lead to numerical issues. Right, so let's have a look at this. Let's create a multinomial regression, do our prediction. So okay, so that's all set up properly, and then we can just do our fit, cultivar in terms of all other things, data equals our training data. Now, because it's a neural net, underlying the hood, underlying things, I may want to set the seed, just so that I get consistent results. Remember that the number of iterations is important to ensuring it converges. So to check convergence, we need to look at the underlying model object. Okay, and so by default this prints this output here, but there's a bunch more stuff inside this object, right? If we have a look at, if I assign that wine.mod object and have a look at it in here, then I can see that it's a list of 26 different things. And if I go and have a look at it, we've got lots of stuff. So we've got the decay, we've got convergence, that's the thing I'm actually interested in. There's a bunch of fitted values and residuals and all sorts of things. Okay, so the thing I want to look at is convergence. Okay, so the pur package is a package to deal with lists, and you'll see here that this is a list, right? It's a list of 26, so that means there's 26 things inside it. And you can see that all those things differ, right? I've got n, which is numeric and only 3 long. I've got n units, which is just an integer that takes the number 18. N con takes 19 different numeric to vector of length 19. Fitted values is numeric, it looks like a matrix. Residuals looks like a matrix. Terms looks like some other object altogether. Weights is a list of 2, or it has dimensions that are a list of 2. So this is sort of a list of a list of a list. So the underlying objects in R are generally lists. So everything is a list. And so pluck is handy because it can pull out things from lists. So in this case we want to pull out the convergent object, and we can do this with our model object with pluck, and we can just pick out convergence. Then it'll pull out that number 0. And we can also do it without the extract fit engine step, because wine.mn is also a list. So the parsnip model object is also a list. And so we could pluck the fit object from that, and then the convergence object from inside that. Okay, and that'll get the same result there. So okay, and I could have found that by just having a look at wine.nm, right? So wine.mn is also a list of 6, and inside that I've got a bunch of stuff, right? I've got level, I've got a specification, let's have a look at other stuff, and I've got a fit. And that fit is then that list of 26, of which convergence is one of them. So I can pull that out with pluck. So it's 0, so it's converged. Yay. Okay. So let's now look at the look at how well it does. So we could augment with the test set. So this just gives us our predictions, and then we could do accuracy. So our truth is going to be our cultivar, and our prediction, our estimate, sorry, is going to be our predicted class. Right, so we've got pretty good accuracy, 95% accurate. Okay, and then we can have a look at the confusion matrix as well to see where we're getting things right and wrong. Okay, so overall we're doing really well. This is an easy data set to classify. We're getting all the A cultivar correct. and getting 3 out of 28 of the B cultivar incorrect as A, and 1 out of 15, 3 out of 28, 3 out of 31 it would be, won't it? 1 out of 15 of the C cultivar incorrect. Okay, so of interest would be how confident the model is in these incorrect answers, right? So we could have a look at that. Okay, so we could have a look at our wine.pred, and we could just filter where the predicted class is not equal to the true class. Okay, and in fact we see that the model is actually super confident. Okay, so here it's with 100% confident, essentially, it is said that this observation here is class A when it was in fact class B, and the same for the others. Okay, so wow, the model is really confident that the ones it's getting wrong are in fact what might be going on. So it might be a good time for you to have a think about what might be going on here. Okay, so why would it be that the model is so confident that these observations are class A when in fact they're not? Okay, now this, as we indicated before, these variables are on quite different scales, and that may affect how well the multinomial package fits things, purely because of numeric issues, right? So in theory, there shouldn't be any difference, because underlying these models is a linear predictor, and scaling things in a linear predictor should make no difference at all, right? It'll just scale the coefficients so that you get the same answer, right? If you multiply a column by 1,000, then all you do is you divide the coefficient of that column by 1,000 and you get the same thing. So let's create a recipe, right, of cultivar in terms of the other things. Where we add a step, normalize all numeric predictors. And we're going to prep that on our training data. Right, so if we have a look at wine.rec, our recipe, we can see that it has centering and scaling for alcohol, malic, ash, and so on and so forth, which has been trained. Okay, now this hasn't actually, we haven't changed the training data at all. It is still the same as what it was. Okay, what we've done is we've worked out how much scaling and centering we need to do. So essentially what we've done is we've worked out the mean of all, of each of these columns, and we've worked out the standard deviation of each of the columns, and the standard deviation, and we're going to subtract the mean and then divide by the standard deviation. And we've stored that information so that when we supply it with a data set, it can then apply that transformation to that data set. Right, so we're going to apply it to the training set, and then of course we're also going to apply it to the test set when we do prediction. Okay, so let's refit the model. So we're going to have multinomial model 2. Okay, and we're going to fit cultivar in terms of everything, and our data now is going to be our baked data. So we're going to take our wine recipe and we're going to bake our training data. And that's going to apply that transformation. Okay, again, we could check convergence. And it's converged. Okay, and then we could do our predictions. Okay, so our predictions, we're going to augment with the new data is going to be the test data. Okay. And then we're going to evaluate how well we do by looking at the confusion matrix. Okay, and something has gone badly wrong, right? Everything is cultivar A. What did I do wrong? You have a think about it. You might want to pause the video and assess. So what I did wrong, of course, is that I supplied the test set, which of course is what I wanted to do, but we've done a transformation, right? We transformed the training set by scaling everything, and I didn't transform the test set. So what I missed was I needed to bake my recipe, right? So that whatever we apply to the training set, we also have to apply to the test set. And then I get something that looks a bit more sensible. And so this looks more promising. We're only getting 2 wrong now. Both cultivar B are one of which is assigned A and the other C. Okay, we might also look at, let's look in detail. Right, we could use that same code that I had before to just have a look at the 2 that are wrong. Okay, so you can see that so the one that we've predicted as being class C, we're actually super confident about it, aren't we? Almost, so basically 100% confident that that's a C, even though it's a B, and we're essentially, 99.6% confident that that other one, that the second row here is an A, even though it's actually a B. Okay. We're still super confident in our incorrectness. What might be going on? Again, have a think about that. And finally, we might want to simplify the model, right? So we could try running a step outside of the tidy models framework, and then incorporating that. So let's perhaps do that quickly. So we're going to have to refit the model using multinom directly, then run step, then refit again in tidy models and evaluate. Okay, so we're going to go multinom. Again, we're going to use the scaled data. So we'll bake our data. So it's going to be bake our delicious recipe. So this is going to be wine.mn3. Right. Multinom. Do we need to maybe load innet? There we go. Right, it's converged after only 60 steps, and by default it gives it 100, so we know it's converged. Okay, and then we want to do predictions. So we want to run step. So let's go mn step. Right, so let's do stepwise regression. So away it's gone, and it's ended up with a model that just has malloc, proline, and flav in it. Okay. So okay, so we'll call this wine.mn4 maybe. All right, so it's going to be a multi-norm regression. Okay, and we're going to fit our cultivar in terms of malloc, proline, and flav. I need to put pluses between these, don't I? And we're going to use our baked training data. Okay, and then we are going to do prediction. So this, I guess, will be our third prediction. Is going to be wine.mn4. And we're going to augment our baked test data. And then we're going to look at our confusion matrix. See how well we do. Oh, so we do quite different indeed. Okay. Okay, so stepwise regression, of course, stepwise improvement is using the AIC to decide whether the model is any good or not. And so the AIC is, of course, trading off model fit and model complexity. And so the stepwise procedure has decided that a much simpler model can explain the data just as well, yet it does poorly on prediction. And that could just be luck. It could just be a situation where actually these three variables are useful for the training set but not so useful by themselves for the test set. Or it could be that some of these are on the threshold, so the predicted classes could be quite close. I guess we could have a look at that. Okay, so we could go wine 3, and we could just filter out where the cultivar is not equal to the predicted class. Okay. Yeah, so some of these we're quite confident. So some of these we're predicting at C with 100% confidence. But some of them were less confident, so 90% confident, and this one here not very confident at all. But most of them were actually pretty confident, right? So it's confidently getting things wrong. And when this happens, it's often because, we saw it back up here as well, it's often because what's actually going on might be that we're actually overfitting the training data. So let's have a look at prediction of the training data. Okay, so let's take our model. So this one here, for example, and we'll augment it this time with our training data. And then do our confusion matrix. And you can see the problem, right? We are 100% fitting the training data. Thus, perhaps we're not generalizing as well, and this explains why the model is super confident about its predictions. Okay, so again, it's another thing to look for when you're fitting models such as neural nets and so on. It's just a sort of sanity check by looking at how well it's doing on the training data. If it's doing really too well on the training data, then maybe it won't generalize as well. It kind of depends on how close the test data is to the training data, which if you know, you have a true test set where you don't know the answer, like for example you have in your assignments, you don't know, right? I guess you can get a feel for it by potentially you could look at the distribution of the predictors in the training set and the distribution of the predictors in the test set to get a sense for how close the test set is to the training set, and you'd hope that it's reasonably close. But I would be a bit nervous, I guess, in practice of applying a model that's essentially perfect on the training data, because what might be happening here is overfitting, right? It's basically we've got quite a complicated model with a lot of parameters, and those parameters have been tweaked essentially too far in that we're perfectly predicting the observations on the training set, but perhaps we won't predict an observation that we should be less confident about. Okay, so here we've got a model that's not getting it perfect on the test set, but is super confident about its predictions. So the predicted probabilities for the ones it's getting wrong are essentially 1. Okay.